All right, so we're going to continue that process, but with different functions. Find the stationary points and state their nature for the following. It says we can use ch10, so that makes life a lot easier. Well, what I might do here is I'll just go through it. Let's find the derivative, dy dx. The derivative of cos is minus sine, so it's minus 2 sine x. And I want to solve that equal to 0, don't I? So in other words, I need negative 2 sine x is equal to 0. Sine x is equal to 0. So where is sine 0? So x is equal to 0, pi, 2 pi, etc. All right, which covers the domain that we're looking at. So they're my turning points. All right, and since we're using our ch, or if we did that graphically now, let's just make that a bit bigger. My cos graph looks like that. Okay, and we need to know turning points. We're saying the turning points are at 0, which is there, pi, which is there, and 0, which is there. So clearly 0 and 2 pi, they're both maximums, and pi is a minimum. All right, x log x, well, that's a little bit harder to sketch. I'm not too sure what that looks like, but let's work out a derivative. F dash of x is equal to derivative of the first, which is 1, times the second, plus the derivative of the second function, which is 1 on x, times the first function. All right, so I've done that quite quickly. So I get natural log of x plus 1. So I've got to solve that equal to 0, which means I get the natural log of x plus 1 is equal to 0. So natural log of x equals negative 1. That's base c, so e to the minus 1 is equal to x. So there's my stationary point, all right, the x coordinate anyway. Corresponding y value, y is equal to e to the minus 1 times the natural log of e to the minus 1, which is just equal to e to the minus 1 times, bring the power at the front, which is negative 1 times, and natural log is log base e of e, which is 1. So I get minus e to the minus 1. So my stationary point is at e to the minus 1, negative e to the minus 1. Okay, so we could check that, the graph of that. The graph of that, if I just do a quick sketch of that graph, it looks a little bit like that. So we can see there that that's the point, e to the minus 1, negative e to the minus 1. So clearly that point there is a minimum. Okay, so this one clearly, when you start having to work with decimal places, it's a calculator active question. So what I've done is I've got a screenshot there of the calculator instructions that I used. First things first was find the values of f dash of x which are equal to 0. So I decided to define the function so I didn't have to retype things. So I've defined the function once, worked out the derivative, all right, and then just solve that expression equal to 0. So my answer here, so if this was for me and it was a test, so I need, so I'd be saying in my SAC, solve f dash of x equal to 0, which means I'd actually write the derivative down. So the derivative is I'd solve the natural log of 2 on 2x minus natural log of 2 on 2 plus a half times 2 to the x equal to 0, and then therefore x is equal to natural log of 2 minus 1 over natural log of 2. Okay, so I guess if it was a 1 mark question, I just put the answer down. If it was 2 marks, I'd probably put the derivative down, which is what I've done there, and then put the answer down. Okay, find the minimum value of f correct to 3 decimal places. So again, I'd be saying I need f of, and I'm going to natural log of 2 minus 1 on natural log of 2. I'm going to put that information in if by chance I've got that wrong, they can see that I've got my answer just by substituting my x value into the function. And to 3 decimal places, I'm going to say it's negative 0.531. Okay, so just that extra little bit of insurance. Again, if it's a 1 mark question, we're just looking for that. So I guess if it's wrong, it's wrong. But just that little bit of information here gives me as a teacher and an examiner an opportunity to understand what it is you're doing. The value of f dashed of 0. So again, I might just rewrite that function again, even though it's a bit of a pain. I'll put natural log of 2 on 2x minus natural log of 2 on 2 plus a half times 2 to the x. And then I might just put a little given x is equal to 0. And therefore, I'm going to put to 3 decimal places 0.153. Okay, so it's not just enough to have your calculator output and just put an answer down. I guess if they were 1 mark questions, you could argue that it's either right or it's wrong. But I think just a little bit of background information gives an examiner an idea of where it is you're heading. All right, so up to our final question. Oh. So let's move it all up a bit. Show that the graph of x blah, 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 has a local maximum at x equal to n. Again, I reckon this is a calculator question, so I'm going to define that function, all right, and then I'll show you the screen output that I get. Okay, so now that I've done the calculator work, let's have a look what I've done. Again, define the function, all right. Again, I think just get in the habit of doing it, because then if I have to graph that function, it's already on the calculator as well. So I have to find a local maximum. I've sort of covered up the question there, where n has a local maximum. So I need where the derivative is 0. So let's find the derivative, which is that. So again, if I had to show that, I'd have said g dashed of x is equal to, what is g dash? It's equal to n on x minus 1 times x to the n e to the minus x. So that's the derivative. So if I solve g dashed of x equal to 0, that gives me x will equal to, from my CAS, it gives me x is equal to 0 or x is equal to n. Okay, so I've got two stationary points there, and n is a positive integer, which we were told. So it's told us to work on the local max. So at x equal to n. Well, if I pick a value just smaller than n, so if I work f dashed of n minus 1, f of x is equal to, which is what I've worked out here. I've worked out, sorry, not f dashed of x is equal to. So if I pick a value smaller than n, so n minus 1, my gradient graph, which is this one here, okay, the gradient is equal to n minus 1 times to the n minus 1 e to the 1 minus n. Now, and since n is greater than, well, it's greater than or equal to 1 because it's a positive integer, all right, that makes all of these expressions positive. E to the power of anything is positive, n minus 1 is positive, n minus 1 is positive. We can just say then that f dashed of n minus 1 is greater than 0. So it's a positive gradient at n minus 1. It's a 0 gradient at n. What is the derivative at n plus 1? Well, n plus 1 is, from my calculator, negative n plus 1 to the n plus 1 times e to the n minus 1. So again, we can say that term there is greater than 0. That term there is greater than 0, but this term here has to be less than 0. Therefore, it's a negative gradient at that point. So at x equal to n, we have a max. So I think more and more likely our exams are getting more this way in terms of working with values of n, and it's relatively straightforward to say show that at x equal to 2 we have a maximum. But I'm thinking that these days they're more interested in getting us to work with general values. So look, it takes a little bit of thought, but the process is the same. How do we find a stationary point? We get the derivative equal to 0, which is what we did here. Solve the derivative equal to 0. All right, so that's where my stationary points occur. How do we work out if they're a maximum or a minimum? We check the derivative either side of that stationary point. So if x is equal to n, a number to the left is n minus 1, a number to the right is n plus 1. All right, so look, have a go through that next example and see how it comes out for you.